software wala, and I'm a student at Rehan School Islamabad campus. So today I'm here with a new Maya. So our today's Maya uh, topic is on explain the cool physics concept in simple term black holes. So let's start our today's Maya. First of all, call the Maya for some questions.
Hey, hey.
Okay, so Maya, my first question from you is what exactly is a black hole in simple words, and how does a black hole form? Please give me answer on this question. Let's start your.
All right. So basically, imagine taking something super heavy, like way heavier than our sun, and squeezing it into a tiny, tiny space. That's what kicks off the whole black hole thing. When you squish enough matter into a small enough spot, gravity goes absolutely wild. It gets so strong that nothing, not even light, can escape its pull. It's why we call it a black hole. It's invisible because light can't bounce off of it. So, how do they actually form? Usually, it's when really massive stars run out of fuel. When this happens, the star collapses in on itself. Gravity wins, and everything gets crushed down into this incredibly dense point called a singularity. That singularity is surrounded by this point of no return called the event horizon. Once something crosses that boundary, it's gone forever. There are also supermassive black holes, which live at the centers of most galaxies, and their formation is still a bit of a mystery to scientists. The prevailing theory is they are formed from smaller black holes merging together over millions of years.
Okay, so that's great, really, and great answer.
What else
So,
are you?
Maya, my next question from you is what are black holes invisible? Please give me answer on this question. Let's start your answer.
So, they're invisible because light itself can't escape them. Black holes are regions of space with such intense gravity that nothing, not even light, can escape once it gets too close. Light bouncing off an object is what allows us to see it, right? But with a black hole, any light that gets close enough is pulled in and can't come back out. Think of it like a one-way street for light. Since light can't escape, we can't directly see the black hole itself. However, scientists can infer a black hole's presence by observing its effect on surrounding matter, like stars getting distorted or pulled in, or by detecting radiation emitted from material as it heats up falling into it. So it's more about spotting what's happening around them than seeing the black hole directly.
That's really
What
great.
specifically about visibility were you
Okay,
wondering about?
okay. So, Maya, my next question from you is what is gravity and why is it too strong in a black hole? Please give me an answer on this question. Let's start your answer, Maya.
Okay, so gravity is basically the force that pulls everything together. Anything with mass, whether it's you, Earth, or a tiny speck of dust, has gravity. The more massive something is, the stronger its pull. So Earth has a strong pull because it's huge. Now, why is it so strong in a black hole? Well, black holes form when a lot of matter gets squished into a really, really tiny space. When you cram that much mass into such a small volume, the gravity becomes intensely concentrated. It's like taking all the gravity of a star way bigger than our sun and squeezing it into something smaller than a city. This creates such extreme gravity that nothing, not even light, has enough speed to escape its pull. It's like why black holes are basically gravity's ultimate weapon. Concentration is everything.
Okay, that's really great. So, my next question from you is what is the event horizon? Please give me very interesting answer on this question. Let's start your answer, Maya. I'm waiting for your answer.
All right. So picture this. You're getting closer and closer to a black hole. There's a certain point of no return, kind of like standing Near the edge of a waterfall, once you go over, there's no swimming back up. That invisible boundary is the event horizon. It's not a physical surface you can touch, but a point where gravity gets so crazy strong that the escape velocity, basically the speed you'd need to fly away, exceeds the speed of light. And since nothing can travel faster than light, nothing can escape the event horizon. It's like a one-way ticket. Here's the cool part. An outside observer would see anything falling and slow down as it gets close to the event horizon, because time itself slows down thanks to the gravity. The object would also appear redder because of the effects of gravity on light. By the time the object crosses the event horizon, it appeared to freeze and fade from view. It's the point where the laws of physics, as we understand them, start to break down.
Okay, so Maya, my next question from you is what is a singularity and are black holes the same size? Please give me a very interesting answer on this question.
Okay, so when you say senior reality, I think you mean singularity. Just wanted to double check there. That's right. The singularity is the very center of a black hole. It's where all that crushed matter ends up. So imagine taking a star many times more massive than the sun and squeezing it down to a point with zero size and infinite density. That's the singularity. It's a place where gravity breaks all the rules and our current laws of physics just don't work there. Now, are black holes the same size? Absolutely not. They come in different sizes, stellar black holes. These are formed from the collapse of massive stars, usually about 10 to 100 times the mass of our sun. Intermediate mass black holes, these are harder to find and are in between stellar and supermassive, about 100 to 100,000 times the sun's mass. Supermassive black holes, these behemoths live at the centers of galaxies and can be millions or even billions of times the mass of our sun. Our own Milky Way has one at its center, so the size depends on how much mass ended up crushed down into that tiny space. Bigger mass, bigger black hole.
Okay, so Maya, my next question from you is uh, that how big can a black hole become? Please give me very interesting answer on this topic. So let's start your answer, Maya. I'm waiting for your interesting answer.
All right, Lewis, so the honest answer? Theoretically, there's no real upper limit to how big a black hole can get. The biggest black holes we know about are supermassive ones sitting at the centers of galaxies, like our own Milky Way. These things can be billions of times the mass of our sun. Honestly staggering. Like some have measured in at 50 billion solar masses or even more. Now there's this idea of ultramassive black holes, even bigger than those. Scientists are still hunting for them. How do they get so massive? Well, they grow over billions of years by gobbling up everything around them. Gas, dust, even other black holes. The biggest known one right now is TON 618, and it's estimated to be around 66 billion times the mass of the sun. It's just mind-boggling to imagine that much mass packed into one spot, creating so much gravity. The more they eat, the bigger they get, theoretically without a known size limit.
Okay, so Maya, my next question
Anything else
from you
about
is can black holes move and how far is the nearest black hole from Earth? So please give me very interesting answer on this.
Okay, so yeah, black holes can absolutely move. They're not just fixed points in space. They can orbit around other stars or galaxies just like anything else with mass. If a black hole formed from a star collapsing, it'll still have the original star's movement before it went supernova. Also, black holes can merge with other black holes, a pretty violent process that sends ripples through space-time called gravitational waves. As for the nearest black hole, The closest known black hole to Earth is called Gaia BH1. It's about 1,560 light years away in the constellation Ophiuchus. It's a relatively small one, only about 10 times the mass of our sun. Another candidate is just 100 light years away, though we're still confirming that. To give you some context, 1 light year is about 6 trillion miles, so they're pretty far. Don't worry about getting sucked in anytime soon.
Okay, so Maya, my next question from you is what happens to a star before it becomes a black hole? So please give me very interesting.
All right, so picture a really massive star, much bigger than our sun. For most of its life, it's like a constant battle between two forces: gravity trying to crush everything inward, and fusion in the star's core pushing outward. Fusion is where hydrogen atoms smash together to make helium and release tons of energy, which is why stars shine. But eventually, the star runs out of hydrogen fuel in its core. When that happens, it starts fusing helium into heavier elements like carbon, then oxygen, and so on, all the way up to iron. Here's the catch: iron fusion doesn't release energy, it sucks it up. This means there's no more outward pressure from fusion to fight against gravity. The star's core starts collapsing in on itself in milliseconds, and the outer layers come crashing down too. This collapse creates a massive supernova explosion, some of the brightest events in the universe. If the star is massive enough, even after the explosion, there's still enough gravity to overcome everything. The core gets squished into this incredibly dense singularity and forms a black hole. Not all stars become black holes, though. Smaller stars just become dense neutron stars or white dwarfs instead.
Okay, so Maya, my next question from you is that every star turn into a black hole? Please give me very interesting answer on this.
No, not every star becomes a black hole. That's actually pretty rare. Only really massive stars end up that way. It all comes down to mass. Our sun, for example, will eventually become a white dwarf, a small, dense remnant of its former self. Think of it like turning down the heat under a pot of water. Lower mass stars do this when they run out of fuel. Black holes form from stars that are at least 20 times more massive than our sun. When these massive stars run out of fuel, they do something dramatic. As discussed, they undergo a supernova, and their core collapses under its own gravity. But stars below that mass threshold don't have enough gravity to overcome everything even after the supernova, so they become white dwarfs, or at a higher scale, neutron stars. It's kind of like only really big trucks being able to make a big dent on concrete versus smaller cars, which have little impact.
Okay, so my next question from you is what role does mass play in a black hole formation and what is a supernova? Please give me very interesting answer.
Okay, so yeah, it sounds like you're asking how mass plays into black hole formation and want me to explain a supernova? Let's break it down. Basically, mass is everything when it comes to black holes, as we've talked about before. The more massive a star, the stronger its gravity. When these very massive stars run out of fuel, gravity can crush everything inward without resistance. The more massive the original star, the more massive the resulting black hole. So there's a direct relationship there. Now, a supernova is what actually happens right before the black hole forms. It's like the star's death throes. When the star runs out of fuel in its core and can't produce enough energy to counteract gravity, the core collapses in on itself. This causes a huge explosion where the star's outer layers are blasted into space as brilliant and colorful explosions. The amount of energy released can briefly outshine entire galaxies. The supernova can then lead to the formation of a neutron star, or if the star was massive enough, a black hole. Does that make sense? Anything else about mass or supernovae you'd like to explore? All right, ready
Okay,
for your next
okay.
question?
My
One
next
more time.
question from you is how long does it take for a black hole to form? So please give me answer.
So it's actually really fast. The whole process from when a massive star runs out of fuel to the black hole fully forming only takes a few seconds. Here's the breakdown. When the core collapses, it happens in milliseconds. The supernova explosion lasts for days to months, but the actual moment of the core collapsing into a black hole is pretty instantaneous. The core implodes and gravity wins in just fractions of a second. Think of squeezing a balloon until it pops. The star that was there moments before ceases to exist as it becomes an infinitely dense point, all within a matter of seconds. It sounds like instant magic when talking about an event that takes billions of years to happen. Pretty wild, right?
Okay, so Maya, my next question from you is could our sun ever become a black hole? And what's the difference between a neutron star black hole? So let's start the answer, Maya.
Nope. Our sun won't turn into a black hole. It's just not massive enough. It's about half the mass of stars needed to go supernova and then become a black hole. When our sun runs out of fuel, it will become a red giant and then eventually settle down as a white dwarf. A neutron star and black hole are both what stars become when they die, but they form in totally different situations. Here's the difference. Neutron star, when a star not massive enough to become a black hole explodes as a supernova, the remain the remaining core gets crushed down into something super dense made of neutrons. Imagine squishing the mass of the sun into something the size of a city. This is a neutron star. It's incredibly dense, but still has some structure and can have magnetic fields. Black hole, these form from really massive stars, the ones where gravity is just way too strong. When the core collapses, it doesn't just become neutrons. Instead, it continues collapsing endlessly into a singularity, a point with no volume and infinite density. It's so dense that nothing, not even light, can escape. Its gravitational pull once past the point of no return, the event horizon. So, neutron stars are incredibly dense, but black holes are infinitely dense, creating a boundary no light can pass through.
Okay, so my next question from you is that can two black holes merge, and what happens when black holes collide?
Yes, two black holes can absolutely merge. In fact, it's thought to be how some of the bigger supermassive black holes in the universe form over time. When two black holes get close enough through orbital movement in galaxies, for example, they start spiraling towards each other. As they get closer and closer, they emit powerful gravitational ripples in space-time. These waves carry energy away from the system, causing the black holes to spiral closer at an accelerating rate. Finally, when they collide, they merge into one single larger black hole. What happens during the merger is pretty wild. The collision creates some of the most powerful events in the universe, releasing huge amounts of energy in the form of gravitational waves. Also, the newly formed black hole briefly oscillates and settles down into a stable shape. That process has been detected multiple times by instruments like LIGO and Virgo. Scientists can feel these ripples travel through space, time, and measure what kind of black holes collided, confirming Einstein's theories of gravity pretty spectacularly. Want to dive deeper into black hole mergers or gravitational waves?
Okay,
All right,
so
what's your next
my
question?
next question from you is: do black holes grow over time, and how do black holes bend space? Please give me very interesting.
Okay, so let's unpack that. Black holes, time, space, and how they're all connected. When it comes to time, black holes really mess with it. The closer you get to a black hole, the slower time passes relative to someone further away. This effect is called time dilation. It's basically what happens when gravity gets really strong. So, for someone watching you fall into a black hole, they'd see you slow down, appear to freeze, and eventually fade away from view as you cross the event horizon. But for you falling in, time would feel completely normal until you were ripped apart. As for how black holes affect space, they warp it. According to Einstein's theory of general relativity, gravity isn't just a force pulling things together, it's actually the curvature of space time caused by mass. Black holes are the most extreme examples of this because they have so much mass packed into such a small space. They create these deep wells in space time that affect the paths of light and matter. Anything that gets too close gets pulled in because it's essentially rolling down this curved space time hill toward the black hole.
Okay, so my next
Want me to
question
expand
from
on
you
any of
is:
that, or are you ready?
what is time dilation near a black hole? Please give me interesting answer on this question. Let's start.
Okay, so that's actually time dilation, not time deletion. Close though. Think about time like a river flowing at a certain rate. Near a black hole, gravity is so intense that it slows down the flow of that river. That's time dilation. Time physically passes slower for someone closer to the black hole compared to someone far away from it. The stronger the gravity, the slower time passes. Imagine you had a clock near a black hole and another one far away. The clock near the black hole would tick more slowly than the one farther away. If you were to fall toward a black hole, from your perspective, time would pass normally for you. However, an observer watching you from a safe distance would see your time slowing down drastically as you got closer. The closer you get to the event horizon, the more extreme this effect becomes. That's because space time gets so warped that time itself stretches or dilates to near standstill. It's like stretching a rubber band. The closer you get to the source of gravity, the more it stretches out.
Okay, so my next question from you is that what is
Anything you
time?
want me to
Sorry, would time completely stop at the event horizon? So please give me.
You mean what happens to time at the event horizon, right? So, as something crosses the event horizon of a black hole, things get weird. From the perspective of an outside observer watching something fall into the black hole, time would appear to completely stop for that object once it hits the event horizon. They would see it slow down more and more as it gets closer and closer, but it would never actually cross the boundary because of the extreme time dilation. That object would effectively freeze there, forever stretched and reddened, but never quite disappearing. However, from the perspective of the person falling into the black hole, they would cross the event horizon and keep falling. Time for them continues as normal until they get stretched and crushed by the intense gravity at the singularity. But to someone watching from afar, that crossing of the event horizon actually never happens. Time stops. So there's this fundamental disconnect. Time stops for external observers at the event horizon, but time continues normally for someone passing through it. It's one of the biggest mind benders about black holes.
Okay, so you this was my. I hope you like it. I will the new my next topic. Like another office.